The weather satellite is a type of satellite that is primarily used to monitor the weather and climate of the Earth. Satellites can be polar orbiting, covering the entire Earth asynchronously, or geostationary, hovering over the same spot on the equator. Meteorological satellites see more than clouds and cloud systems. City lights, fires, effects of pollution, auroras, sound and dust storms, snow cover, ice mapping, boundaries of ocean currents, energy flows, etc., and other types of environmental information are collected using weather satellites. Weather satellite images helped in monitoring the volcanic ash cloud from Mount St. Helens and activity from other volcanoes such as Mount Etna. Smoke from fires in the western United States such as Colorado and Utah have also been monitored. Other environmental satellites can detect changes in the Earth's vegetation, sea state, ocean color, and ice fields. For example, the 2002 Prestige oil spill off the northwest coast of Spain was watched carefully by the European ENVISAT, which, though not a weather satellite, flies an instrument which can see changes in the sea surface. El Niño ±0 and its effects on weather are monitored daily from satellite images. The Antarctic ozone hole is mapped from weather satellite data. Collectively, weather satellites flown by the US, Europe, India, China, Russia, and Japan provide nearly continuous observations for a global weather watch. History. As early as 1946, the idea of cameras in orbit to observe the weather was being developed. This was due to sparse data observation coverage and the expense of using cloud cameras on rockets. By 1958, the early prototypes for TIROS and Vanguard were created. The first weather satellite, Vanguard 2, was launched on February 17, 1959. It was designed to measure cloud cover and resistance, but a poor axis of rotation and its elliptical orbit kept it from collecting a notable amount of useful data. The Explorer 6 and 7 satellites also contained weather-related experiments. The first weather satellite to be considered a success was TIROS-1, launched by NASA on April 1, 1960. TIROS operated for 78 days and proved to be much more successful than Vanguard 2. TIROS paved the way for the Nimbus program, whose technology and findings are the heritage of most of the Earth-observing satellites NASA and NOAA have launched since then. Beginning with the Nimbus 3 satellite in 1969, temperature information through the tropospheric column began to be retrieved by satellites from the eastern Atlantic and most of the Pacific Ocean, which led to significant improvements to weather forecasts. The ESSA and NOAA polar orbiting satellites followed suit from the late 1960s onward. Geostationary satellites followed, beginning with the ATS and SMS series in the late 1960s and early 1970s, then continuing with the GOES series from the 1970s onward. Polar orbiting satellites such as KickSat and TRMM began to relay wind information near the ocean's surface starting in the late 1970s, with microwave imagery which resembled radar displays, which significantly improved the diagnoses of tropical cyclone strength, intensification, and location during the 2000s and 2010s. Observation. Observation is typically made via different channels of the electromagnetic spectrum, in particular, the visible and infrared portions. Some of these channels include visible and near-infrared, 0.601 ma euro 1.601 ma euro for recording cloud cover during the day, infrared, 3.9 ma euro 7.3 m, 8.7 m, a euro 13.4 m. Visible spectrum equals visible light images from weather satellites during local daylight hours are easy to interpret even by the average person. Clouds, cloud systems such as fronts and tropical storms, lakes, forests, mountains, snow ice, fires, and pollution such as smoke, smog, dust and haze are readily apparent. Even wind can be determined by cloud patterns, alignments and movement from successive photos. Infrared spectrum equals, the thermal or infrared images recorded by sensors called scanning radiometers enable a trained analyst to determine cloud heights and types, to calculate land and surface water temperatures, and to locate ocean surface features. Infrared satellite imagery can be used effectively for tropical cyclones with a visible eye pattern, using the Dvorak technique, where the difference between the temperature of the warm eye and the surrounding cold cloud tops can be used to determine its intensity. Infrared pictures depict ocean eddies or vortices and map currents such as the Gulf Stream, which are valuable to the shipping industry. Fishermen and farmers are interested in knowing land and water temperatures to protect their crops against frost or increase their catch from the sea. Even El Niño plus or minus O phenomena can be spotted. Using color-digitized techniques, the gray-shaded thermal images can be converted to color for easier identification of desired information. Types. Each meteorological satellite is designed to use one of two different classes of orbit, geostationary and polar orbiting. Geostationary equals. Geostationary weather satellites orbit the Earth above the equator at altitudes of 35,880 kilometers. Because of this orbit, they remain stationary with respect to the rotating Earth and thus can record or transmit images of the entire hemisphere below continuously with their visible light and infrared sensors. The news media use the geostationary photos in their daily weather presentation as single images or made into movie loops. These are also available on the city forecast pages of Noaa.gov. Several geostationary meteorological spacecraft are in operation. The United States has 3 in operation: GOES-12, GOES-13, and GOES-15. GOES-12, previously designated GOES East and now used for South America, is located at 60 degrees west. GOES-13 took over the role of GOES East on April 14, 2010 and is located at 75 degrees west. GOES-11 was GOES West over the eastern Pacific Ocean until it was decommissioned December 2011 and replaced by GOES-15. Russia's new generation weather satellite Electro-L1 operates at 76 degrees over the Indian Ocean. The Japanese have the MTSAT-2 located over the mid-Pacific at 145 degrees E and the Himawari 8 at 140 degrees E. The Europeans have Meteosat 8 and Meteosat 9 over the Atlantic Ocean and have Meteosat 6 and Meteosat 7 over the Indian Ocean. India also operates geostationary satellites called INSAT which carry instruments for meteorological purposes. China operated the Fengyun geostationary satellites FY2D at 86.5 degrees E and FY2E at 123.5 degrees E, which are no longer in use. Polar orbiting equals. Polar orbiting weather satellites circle the Earth at a typical altitude of 850 km in a north-to-south path, passing over the poles in their continuous flight. Polar satellites are in sun-synchronous orbits, which means they are able to observe any place on Earth and will view every location twice each day with the same general lighting conditions due to the near-constant local solar time. Polar orbiting weather satellites offer a much better resolution than their geostationary counterparts due to their closeness to the Earth. The United States has the NOAA series of polar orbiting meteorological satellites, presently NOAA-17 and NOAA-18 as primary spacecraft, NOAA-15 and NOAA-16 as secondary spacecraft, NOAA-14 in standby, and NOAA-12. Europe has the Top A and Top B satellites operated by EUMETSAT. Russia has the Meteor and Resurse series of satellites. China has FY1D and FY3A. India has polar orbiting satellites as well. DMSP. The United States Department of Defense's meteorological satellite can see the best of all weather vehicles with its ability to detect objects almost as small as a huge oil tanker. In addition, of all the weather satellites in orbit, only DMSP can see at night in the visual. Some of the most spectacular photos have been recorded by the night visual sensor. City lights, volcanoes, fires, lightning, meteors, oil field burn-offs, as well as the aurora borealis and aurora australis have been captured by this 450-mile-high space vehicle's low moonlight sensor. At the same time, energy use and city growth can be monitored since both major and even minor cities, as well as highway lights, are conspicuous. This informs astronomers of light pollution. The New York City blackout of 1977 was captured by one of the night orbiter DMSP space vehicles. In addition to monitoring city lights, these photos are a life-saving asset in the detection and monitoring of fires. Not only do the satellites see the fires visually day and night, but the thermal and infrared scanners on board these weather satellites detect potential fire sources below the surface of the Earth where smoldering occurs. Once the fire is detected, the same weather satellites provide vital information about wind that could fan or spread the fires. These same cloud photos from space tell the firefighter when it will rain. Some of the most dramatic photos showed the 600 Kuwaiti oil fires that the fleeing army of Iraq started on February 23, 1991. The night photos showed huge flashes, far outstripping the glow of large populated areas. The fires consumed millions of gallons of oil. The last was doused on November 6, 1991. Uses, snowfield monitoring, especially in the Sierra Nevada, can be helpful to the hydrologist keeping track of available snowpacks for runoff vital to the watersheds of the western United States. This information is gleaned from existing satellites of all agencies of the U.S. government. Ice flows, packs and bergs can also be located and tracked from weather spacecraft. Even pollution, whether it is nature-made or man-made, can be pinpointed. The visual and infrared photos show effects of pollution from their respective areas over the entire Earth. Aircraft and rocket pollution, as well as condensation trails, can also be spotted. The ocean current and low-level wind information gleaned from the space photos can help predict oceanic oil spill coverage and movement. Almost every summer, sand and dust from the Sahara Desert in Africa drifts across the equatorial regions of the Atlantic Ocean. GOES East photos enable meteorologists to observe, track and forecast this sand cloud. In addition to reducing visibilities and causing respiratory problems, sand clouds suppress hurricane formation by modifying the solar radiation balance of the tropics. Other dust storms in Asia and mainland China are common and easy to spot and monitor, with recent examples of dust moving across the Pacific Ocean and reaching North America. In remote areas of the world with few local observers, fires could rage out of control for days or even weeks and consume millions of acres before authorities are alerted. Weather satellites can be a tremendous asset in such situations. Nighttime photos also show the burn-off in gas and oil fields. Atmospheric temperature and moisture profiles have been taken by weather satellites since 1969. See also: Earth Observation Satellite, List of Earth Observation Satellites. Geostationary Orbit, Low Earth Orbit, Satellite Temperature Measurements. References. External links, Theory, Ralph E. Taggart. Weather Satellite Handbook. Newington, Connecticut, American Radio Relay League. ISBN 0-87259-448-3. Cooperative Institute for Meteorological Satellite Studies Drive Verna Suomi Biography, Interpreting Satellite Images Suomi Virtual Museum. Physical Characteristics of Geostationary and Polar Orbiting Weather Satellites, NOAA Economics and Social Benefits of POES. Data, Near Real-Time Composite of Satellite Image of the Earth by Intellicast, International Weather Satellite Viewer Online Geostationary Weather Satellite Viewer with 2 months of archived data. Earth at Night by NASA, EUMETSAT the European Organization for the Exploitation of Meteorological Satellites, NASA Langley Cloud and Radiation Research Near Real-Time and Archived Satellite Imagery and Cloud Products. Government Policy, Geostationary Weather Satellites, Progress Made, but Weaknesses in Scheduling, Contingency Planning, and Communicating with Users Need to be Addressed, Report to the Committee on Science, Space, and Technology, House of Representatives Government Accountability Office, Polar Weather Satellites. NOAA identified ways to mitigate data gaps, but contingency plans and schedules require further attention. Report to the Committee on Science, Space, and Technology, House of Representatives Government Accountability Office.